Hi guys, welcome to this session of using lens formula to calculate the required focal length or power of corrective lenses to address common eye defects such as myopia, short-sightedness, and hypermetropia, farsightedness. To find the corrective lens, we can find the specifications of the lens required to bring objects into focus on the retina. Let's understand the concept of the far point and near point in the human eye. Let's begin with the far point. The far point is the farthest distance at which the eye can see an object clearly without any strain. For a normal eye, the far point is at infinity because a normal eye can focus on very distant objects. In myopia, short-sightedness, the far point is closer than infinity. Example, 2 meters, 50 centimeters extra, meaning the person cannot see objects clearly beyond this distance. This occurs because the eye's lens or cornea focuses light in front of the retina. Correction: a concave diverging lens is used to shift the far point to infinity. Let's understand the working of a normal eye. Have you wondered why the eye is able to focus the images of objects lying at various distances? It is made possible because the focal length of the human lens can change, i.e., increase or decrease, depending on the distance of objects. It is the ciliary muscles that can modify the curvature of the lens to change its focal length. The image is formed on retina for a normal eye. Myopia, short-sightedness. Myopia is a defect of vision in which a person clearly sees all the nearby objects, but is unable to see the distant objects comfortably, and his eye is known as a myopic eye. A myopic eye has its far point nearer than infinity. It forms the image of a distant object in front of its retina. A concave lens has an ability to diverge incoming rays. It is used to correct this defect of vision. Near point. The near point is the closest distance at which the eye can see an object clearly without any strain. For a normal eye, the near point is at 25 centimeters for a young adult with healthy vision. This distance is referred to as the least distance of distinct vision. In hypermetropia, farsightedness, the near point is farther than 25 centimeters. Example, 50 centimeters, 100 centimeters, etc., meaning the person cannot see objects clearly at a close range. This happens because the eye's lens or cornea focuses light behind the retina. Correction: a convex, converging lens is used to bring the near point closer to 25 centimeters. Hypermetropia, long-sightedness, is a defect of vision in which a person can see distant objects clearly and distinctively, but is not able to see nearby objects comfortably and clearly. Here the image is formed behind retina. A hypermetropic eye has its least distance of distinct vision greater than 25 centimeters. Since a convex lens has the ability to converge incoming rays, it can be used to correct this defect of vision. Recall lens formula and its use to calculate power of corrective lenses. Power of lens is defined as the reciprocal of its focal length. It is represented by letter P. The degree of convergence or divergence of light rays achieved by a lens is expressed as power. The SI unit of power of a lens is diopter. Focal length of the corrective lens in meters or centimeters. Image distance, usually the eye's far point for myopia or near point for hypermetropia. Object distance, typically infinity for distant vision correction or 25 centimeters for near vision correction. Myopia, short-sightedness. Problem. A myopic eye can focus on near objects, but distant objects appear blurry because the eye's lens focuses light in front of the retina. Corrective lens. A concave diverging lens shifts the focus back onto the retina. How the lens formula is used. Image distance is the far point of the myopic eye, negative value. Solve for using the formula to find the focal length of the concave lens. Example for myopia. If the far point of a myopic eye is 50 centimeters, the lens formula becomes object distance is infinity as distant objects are being viewed. Image distance is the far point of the myopic eye, negative value. Here 50 centimeters. Hypermetropia, farsightedness. Recall lens formula and power of a lens. Problem. A hypermetropic eye can see distant objects clearly, but near objects appear blurry because the eye focuses light behind the retina. Corrective lens. A convex, converging lens shifts the focus forward onto the retina. How the lens formula is used. Object distance U is the desired near point. Example. 25 centimeters for normal vision, negative because it's on the same side as the lens. Image distance V is the near point of the hypermetropic eye, positive value. Solve for F to find the focal length of the convex lens. Example for hypermetropia. If a person's near point is 100 centimeters, the lens formula becomes object distance U is the desired near point, i.e. 25 centimeters for normal vision. Image distance V equals 100 centimeters is the near point of the hypermetropic eye. Calculate F and then power of lens. Let's discuss and solve questions based on the discussed concepts. The far point of a myopic eye is 50 centimeters. What is the nature and power of the corrective lens required? Recall, to correct a myopic eye, a diverging concave lens is used. Given data, far point of the myopic eye V equals minus 50 centimeters, negative because the far point is virtual and on the same side as the lens. Object distance U equals infinity, since we are correcting vision for distant objects. Step 1. Lens formula to find the focal length of the concave lens. Put V equals minus 50 centimeters and U equals infinity. F is minus 50 centimeters 0, or minus 0.5 m. Then calculate the power of the using the discussed formula, minus 2 diopter. Here is the result. Nature of the lens, diverging concave lens. Power of the lens, minus 2 diopter. The lens should enable the person to see distant objects clearly by shifting the far point to infinity. Let's explore one more question. A short-sighted person cannot see clearly beyond 2 meters. Calculate the power of lens required to correct his vision. To correct short-sightedness, myopia, the person needs a diverging concave lens. Given data, far point of the person's IV equals minus 2 meters, negative because it's virtual. Object distance U equals infinity, since we are correcting vision for distant objects. Substituting V equals minus 2 meters and U equals infinity, we obtain the focal length of the required concave lens as minus 2 meters. Now let's calculate the power of lens as reciprocal of F. Here power is minus 0.5 diopter. Final answer. Nature of the lens, diverging concave lens. Power of the lens, minus 0.5 diopter. The lens should help focus distant objects, effectively at infinity, onto the retina. One more questions. A myopic person having far point 80 centimeters uses spectacles of power minus 1.0 diopter. How far can he see clearly? Given power of the lens equals minus 1.0 diopter. Far point of the person V equals minus 80 centimeters. Negative because the image is virtual. Object distance U equals new farthest object distance they can see clearly. From the given power of lens, let's calculate the focal length F as minus 100 centimeters. Then using v equals minus 80 centimeters, let's calculate image distance using lens formula. U is calculated as minus 400 centimeters. The spectacles allow the myopic person to see distant objects clearly up to 400 centimeters for meters. So guys, remember lens formula, power as reciprocal of focal length, and concept of far point and near point to find the power of corrective lenses. Try these questions yourself and can request solutions in comments or share solution with the community. All the best. Be optimist, kick off the sorrow. Surely future will be yours tomorrow. Thank you guys for watching video. Please don't forget to subscribe to my channel. All the best for exams in advance from Paradise Coaching. Also, please do like, share the video, and subscribe to my channel. Thank you once again for watching the video.